Last week we focused on confidence intervals for categorical data, so trying to estimate a population proportion. This week we're shifting over to quantitative data, trying to estimate a population mean. So we're coming back to this body temperature example. Body temperature is often thought to be 98.6 degrees. Is that really the average? So we have data for 65 healthy female volunteers, 18 to 40, that were participating in vaccine trials. And the sample mean for this group is 98.4 degrees, and the standard deviation is 0.743. So we're going to use symbols for that. So for the sample mean, we write that as x bar, so that's 98.4. And the sample standard deviation, we write that as just s, so that's 0.743. And these numbers are both just describing the individuals in the sample. So the mean is saying that the average body temperature for these 65 people is 98.4, and the standard deviation is saying that on average, the individual body temperatures in this sample vary from the mean by 0.743. So this is a measure of the sample spread. And we want to use this to estimate the population mean. So when we're talking about the population mean, that's a parameter. So we're going to use the Greek letter mu for that. So mu is the average body temperature in the population, and we're going to kind of try to think about which population we might be able to generalize to. So this will be for females 18 to 40 in the population. Working with categorical data, we learned the 2SE method, and the same basic formula also applies for quantitative data. We're just plugging in different values. So let's start off with the statistic. We've got our sample statistic, which is x bar, or the sample mean, plus or minus the multiplier. Since this is a 2SE interval, for now we're just going to use 2 as our multiplier. And we want the standard error of our sample statistic x bar, and the formula for that is s over the square root of n. Okay, so plugging that in, we've got 98.4, that's our sample mean, plus or minus 2, and then we're going to take our standard deviation, 0.743, and we're going to divide that by the square root of n, so the square root of the sample size, square root of 65. So really quick before we go further here, let's think about the standard error of the statistic. So we're dividing it by the square root of 65, so the standard error is going to be much smaller than the sample standard deviation. So take a second and think about, why does that make sense? Why is the standard error so much smaller than the standard deviation? So remember, when we talk about the standard error, that doesn't describe the variability of the sample, that describes the variability of the statistic. And the sample mean is going to be a lot less variable than the population overall, right? So you might have one healthy person who has a body temperature of 100 degrees, whereas if you look at an average, if you take 65 people, 65 healthy people, and calculate an average, it would be extremely unlikely to get an average of 100, right? Things tend to balance out with averages, and so the sample means are much less variable than the sample itself. So you can see based on the formula that the standard error is always less than the standard deviation. Okay, so putting all of this together, we get a range of 98.216 up to 98.584. So what we've done here is we've started off with our sample statistic. We started off with x bar, and we added and subtracted the margin of error. So two standard errors together, that makes the margin of error. And then what we ended up with on this end is the range of plausible values for mu. So basically we're saying that we think that the population mean could be anywhere between these values. And to interpret that, we say we're 95% confident that our interval, so our interval from 98.216 up to 98.584, that interval is going to capture our true parameter. So captures, and then we want to write the parameter in context. So here that would be the average body temperature for females 18 to 40, and we're talking about healthy females, of course, females 18 to 40 in the population. So a quick pause to think about the generalizability of this statement. So let's say that this sample isn't actually representative of females 18 to 40 in the population. So for example, one thing that can happen with medical trials is that a lot of times the people who are participating are almost too healthy, right? They don't have like any conditions, any health conditions, and that's actually somewhat unusual in the population. So let's say that these people aren't representative. Is that a concern, or is that something that the margin of error takes care of? Unfortunately, the margin of error cannot fix that problem. So if your sample is not representative, then the margin of error isn't going to fix it for you. The margin of error only accounts for sampling variability. So this is only as valid as our sampling method. If we don't have a good representative sample, then our results aren't generalizable. Okay, so that was the 2SE method, and that works pretty well as long as you have 95% confidence. But let's say that we wanted to change the confidence level. For that, we would need a theory-based approach. And the theory-based approach that we use when we're talking about one mean is called a one-sample t interval. Remember, t is when you have quantitative data, z is when you have categorical data. So the way that the t-distribution comes into play is that's how we're going to calculate our multiplier. So the multiplier tells us how many standard errors we need to add and subtract on each side. So the 2SE method says that for 95%, it needs to be about 2. If we calculate it with the t-distribution, it's not exactly 2, but it's going to be very close. So basically, similar to what we did with categorical data, we're going to think about what we need to do to capture 95% of outcomes. And this value that gives us the 95% is called T star. For categorical data, we called it Z star. Here we're calling it T star. And your T star value does change a little bit depending on the sample size. Remember, there's different versions of the T distribution based on degrees of freedom, which is the sample size minus 1. So how does T star compare to Z star? So T star is always going to be a little bit larger than Z star, and so this leads to a wider confidence interval. And if you think about why that makes sense, notice here that we're having to estimate more than one thing. We have to estimate both the sample mean and the sample standard deviation and use those in our formula. Whereas with categorical data, the only thing that we had to estimate was the proportion. So because we're estimating both of these values, it's adding in a little bit of extra uncertainty, and that's going to make our confidence interval wider. However, T star does start to look more like Z star as the sample size gets larger. And this sort of makes sense too. As your sample size gets larger, your sample standard deviation becomes a better and better estimate of your population standard deviation, and so that extra uncertainty isn't as much of a big deal. So here you can see the calculation of the one sample t interval. It looks almost exactly like what we did before, except instead of using 2, we're using 1.9977, and this comes from the t distribution. That's where we got this multiplier. But of course, it's extremely close to 2, and so you're going to end up with roughly the same outcome. And because we're using a theory-based approach, we do need to check the validity conditions. These are going to be the same as the conditions we used for a hypothesis test with quantitative data. So if you remember from a one sample t-test, what we were looking for was two things. One, we wanted to look at the sample size. So in this case, the sample size is 65, which is bigger than the cutoff we usually think of, which is 20. So our sample size is bigger than 20. And we also need to consider the shape, right? 20 is only big enough if your data are not strongly skewed. So I'm going to go back up here and look at the sample distribution. Yeah, not strongly skewed at all. It looks really nice and bell-shaped. So this would have probably been okay even if the sample size was small. I think definitely with a sample size of 65, we should be good here. So the sample size is bigger than 20, and the sample data are not strongly skewed. So we always have to look at that in the graph. Not strongly skewed. And so in this case, our validity conditions are met, which means that it's valid to use the one sample t interval here. So instead of showing you how to get T star, where you would still have to plug everything into the formula by hand, I'm just going to show you how to do this really quick with an applet. So let's use the theory-based inference applet. Here we're going to change the scenario from one proportion to one mean, since we have quantitative data now. Our sample size was 65. Our sample mean, X bar, was 98.4. And our sample standard deviation, S, was 0.734. So I click calculate here, and then I choose confidence interval, and by default it gives me the 95% confidence interval, and you can see I'm getting the same answer there. So all the same principles that you learned earlier, the only difference is that now we're talking about means instead of proportions, and that changes the mechanics of the calculations a little bit.